So the second model of this chapter is a two-sided search model of unemployment. So we're going to talk about the same issue. So unemployment. Okay, so you have already seen a model that determines the reservation wage and the unemployment rate, right? The key there, the final variable that we really care about should be the unemployment rate. Okay. Here, it is also going to talk about the unemployment rate, but we're going to change the model by a lot. Okay. First of all, this one is going to be a one-period model. So this is a large difference, right, from infinite time horizon model to a one-period model. The reason why we do so is because we want now to focus not just on the employee side, but also on the employer side. So we now have N consumer who can all potentially work. So basically N is the working age population, like we defined before. And the number of firms here is actually an endogenous variable. Or you can think of it as there are fixed number of firms, but this firm can decide whether they want to hire or not. They want to hire someone or not, or open a job opening or not. And the number of job opening is what we define as the number of firms. So we say another way to put this is that the number of active firm is endogenous. Okay, and here the consumer, we have N consumer, and each of these consumer will choose whether to work outside the home market or to search for work in the market. Okay, so this kind of outside the market work is you can consider as something like a housework. Okay, you do it at your own house, you can still make some money. Okay, you can either choose to work like this, or you can choose to search for work in the market. The capital Q is the number of consumer who actually choose to search for work. So N minus Q is not in the labor force. Okay, and P of Q is the expected payoff to searching for work that would induce Q workers to search. Okay, so P stands for the payoff. P of Q, so given any Q, P of Q gives me the payoff that will exactly induce number of Q workers to work. So think of it as a supply curve of the searching worker. Okay, so I don't know if that's clear enough, but take a look at this graph. Okay, so now the x-axis here is the Q, labor force, number of labor force. Here is the expected payoff searching for a job. Okay, so given some number of payoff will induce, so this is P star, okay, payoff is P star, will induce some Q star number of worker, right? P of Q is just describing the relationship of this. Okay, so think of P as the price. The reason why we say that this is a work like a supply curve is because if the price is that high, that many workers will come out and search for a job. If the payoff is even higher, the price is even higher, the benefit of searching for a job is even higher. There will be more workers searching for a job, right? So the relationship is a positive correlation. Okay. And okay, so for the marginal worker, when I say marginal, I mean basically this Q star, there are Q star, so say Q star is 10 people, the last person who joined the labor force. Okay, because when P is lower, maybe there's only one person here. Now there's 10 people. So it must be the first person joined me, second people join the labor force, third people join the labor force. And the marginal meaning the last person. Okay, the last person, his housework payoff is should be exactly the same as this P star, because he's indifferent between searching for a job or doing the housework, right? For the other 9 people, the expected payoff must be higher than the housework payoff. And for firms will post a vacancy in order to have a chance to matching with a worker. Okay. And there's some cost for posting this vacancy. Okay, this is like the 104.com. If you are a firm, you post a job on 104.com, you actually have to pay for a fee. Or LinkedIn, if you want to hire someone on LinkedIn, I think there's a free 1 post or 2 posts that you can use. But your account, after that, if you want to hire more people, you have to pay for the job opening you post there. So the cost for posting one vacancy is this K. This K. Okay. And the capital A is the number of active firms. So firm who post a vacancy. We basically assume that one firm can only post 1 vacancy. Okay. But if you think that's unrealistic, consider it as if there's one big firm that can post a lot of vacancy. Consider it as one firm but different department. And each department are considered as one firm. Okay, it's the same. Doesn't really matter that much. So we consider one firm here just can post 1 vacancy. So there's a matching mechanism here. Basically, say the actual aggregate number of matches. There are Q number of Q is the people who search for a job, right? And the A is the vacancy. This is vacancy. This is search job people. That many Q number of people are searching for a job. A number of people are, A number of vacancy are there. How do we decide how many people are actually matched here? When I say match, I mean 1 vacancy is matched with 1 person. That is a match. Okay. So by the way, this model, if you change it a little bit, it can become a marriage market matching model. Okay, it's actually all the same. Just change the label of employer and employee. Okay, but you need to, you can consider whether the female or the male would be the employer or the employee. Okay, so that's the tricky part. Okay, so if there are Q number of people searching for a job and A vacancy, in this model we use a very simple function to decide how many matches there will be. So the Q and A will enter a function that's called a matching function, M. This M is a matching function. This matching function will then times a matching efficiency, how efficiency the matching will be. High efficiency meaning that most job will be matched with each other. Vacancy and the person who's searching for a job will find each other. Okay. And then this E times M of QA will become the total number of aggregate number of matches. Okay, so this is like if 10 people are looking for a job and maybe there are 20 job vacancy. And this M of 10, 20 maybe will give you something like 9. And this efficiency may be half. And then the total number of aggregate matches will be 4.5. Okay. And to make our life easier, this matching function works just like the production function we already see in the chapter 4 or chapter 5. Consider Q and A as the input and M as the output. Then this lowercase e just play as the same role as the total factor productivity, or Z, in the production function. And the matching function is also constant return to scale, meaning that if you double the Q and the A at the same time, then the number of matches will be double. Okay. That makes sense, right? If double the vacancy and double the number of people who search for the job, then the total number of people who get a job will be double. Okay. And there's a positive marginal product and diminishing marginal product, meaning that if you increase either Q or A, you will increase the match, but the increase is decreasing. The slope is decreasing. Okay. And now let's focus on the supply side of the labor market in here. So basically, we're doing the optimization problem for the consumer. So each consumer choose between either this home production, housework, or search for a job. The consumer, if they choose to search for work, then he or she finds a match with a firm with probability PC. PC is the probability that you will find a job. And what is PC? PC should be E times this matching function divided by Q, right? Because this is how many matches in total there will be. How many people actually find a job. And Q is what? Is how many people are searching for a job. So if 10 people are searching for a job and there's only 5 matches, then the chance that I will find a job will be half. Right? Because we consider here everybody are equally the same. So there's no way that, you graduate from NTU and some other people not graduate from NTU, so you get a higher chance. Everybody's chances are equal. So if there are 10 people looking for a job and 5 people eventually match, then at least prior to actual matching happening, beforehand, you know that the chance you will get a match is half. But remember, this function, M, the matching function, is constant return to scale. And if it is constant return to scale, this Q can go into this function. And Q divided by Q is 1, and A divided by Q is this. Right? We are utilizing the fact that this function M is constant return to scale. That's the key here. And we define this thing. This thing is called the, didn't talk about here yet, but we defined this as J. J stands for jamming. Is how jamming this labor market is. Okay. So if the consumer search for a work and is matched, he or she will receive a wage W. We assume here wage W is a constant. Everybody get the same wage. If he's not matched, then he will get the unemployment insurance B, as in the previous model. Then this should be a very simple optimization to do, right? There's PC chance that you'll find a job. If you find a job, you will get W. There's 1 minus PC, you will not find a job. Then you will get this unemployment benefit B. And you can rewrite this as B plus EM1J W minus B. Because PC is, because this is PC, basically. Okay? And what is this? This is the expected payoff that you get right? This is the expected payoff. Probability times payoff, probability times payoff. This is the expected payoff. But I define expected payoff as this, right? P of Q. Here, remember, this J is A divided by Q. This is where Q entered this function. So, as the Q increase, the expected payoff must be what? Okay, by the way, I mean, this is what actually right on the textbook. It says that J is the labor market tightness, but tightness, jamminess, I mean, it's the same thing. Okay, how tight or how jamming the market is. J is A divided by Q. Not clear to you guys what happened when Q increased? Q increase, this whole thing will decrease, right? Or put it another way, when Q increase, the matching chance must be lower, right? And W minus B must be a positive number. Otherwise, I won't accept the offer, right? So the whole thing must decrease. Get what I'm saying? Okay, if it is not clear, let's look at this. This is the supply side of the labor market. Okay. Here, this is the labor force, Q. Here is the equation I just wrote. B plus E times M of 1J and W minus B. This is the expected payoff. So I was writing this P of Q here, but P of Q exactly equal to these things. So I know the exact form of this expected payoff. Is that clear? Okay, so when Q is higher, it must be the case that the chance is lower, right? The chance, when the Q is higher, the chance that you actually get a match must be lower. Because M1J is, so when Q increase, this J decrease. Right? Q increase, meaning there are more people trying to find a job. Do people understand what I'm saying right now? Okay. When Q increase, this J decrease. But with this J decrease, this matching function is a constant return to scale and marginal product is positive. Marginal product of one or this both attribute is positive. So it must be the case that this thing is decrease. If this thing decrease, that means the chance, the benefit, the expected payoff is actually going to be lower. It must be the case I need to increase something else to keep it, the equation equal, right? So it must be increase the W, basically. Okay. If you don't know what I'm talking about, we'll talk about that later. Okay. So here, I want you to get, what really get out of this is that we can actually get a function form of this P of Q, which is B plus this EM1J and times W minus B. Demand side of the labor market is very similar. A firm entering the labor market bears the cost K opposed to vacancy. And the probability that a firm with a vacancy actually find a worker to fill the job is what? We define it as PF. Now it's the opposite, right? The total number of matches is still EMQA. That's the total number of matches. But the denominator become A. So from the firm's perspective, there are 10 vacancies. And eventually there will be 8 matches. That means 8 out of 10, there's an 80% chance the job offer that I post will actually get some person to fill this vacancy. Right? It's simple math. Also, the firms are all the same. That's why it's just a simple divided math. And again, because this thing is what? Is constant return to scale. This A can go inside and this will become EM and Q of Q divided by A and 1. And AQ is J, so Q divided by A will be 1 over J. If someone is matched, a worker and a firm will together produce Z. So the production is Z. Okay, so to the firm, his payoff will be Z minus W. W is his cost of hiring this person. We haven't considered the vacancy, posting the vacancy cost. But for the firm, actually got someone who's capable of working, then he will produce Z, and then the cost is W, so Z minus W. So in equilibrium, the net payoff of posting a job must be 0. This is just ensuring that this is perfectly competitive market so that the firm will get 0 profit. Okay, so it must be the case that probability PF that you will actually, this job will be filled, then you will earn Z minus W, and then minus the posting cost K, the net payoff will be 0. And if you get this, then this will imply that EM J of 1 over J1 will equals, basically this is PF, right? PF is this. PF will become K divided by Z minus W. Okay, so basically, this is a function of J, right? Here, I write something a little bit different. What I write here is the labor market tightness, J. This is J. And here, I write K divided by Z minus W. And the relationship between these two things is basically this function. This is the relationship, right? So if I define this as the Y variable and this is the X variable, then the relationship would basically be EM 1 over J1. So that's why I write EM 1 over J1 here. I changed the label by a bit so that otherwise, I won't get the x-axis as J here. The reason why I need it here is because it will then tells me the tightness, which is the key variable here. Okay? Okay, so one last thing that we haven't really decided is that how the wage is actually determined. Okay, we actually need to use something called a Nash bargaining theory to determine how the matched firm and the workers split the total revenue from production. The simple story goes like this. So the workers' surplus is W minus B. That's what he earned in addition to the unemployment insurance. And the firm's surplus, Z minus W, is profit. So the total surplus is Z minus B. So wage is something between Z and B, right? Wage is something in between. So how the wage is going to decide? Wage is basically a linear combination of Z and B. Okay, and this A is basically workers' share of total surplus. Okay, so you can define it as WB as the A times Z of Z minus B. That's the total surplus. This is workers' share. But if you rewrite this, it's basically a linear combination of Z and B. So the higher the A, the wage will be closer to the production. The lower the A, the wage will be closer to the benefit B. Okay? Now if we put this W equal AZ plus 1 minus AB back into the equation that we got from supply side and demand side. This is the supply side. This is the demand side equation we already have from the slides before. We have W here and W here, right? And we plug this here and plug this here. Then what we see, what we get would be these two equations. PQ will be B plus EM1J and times A times Z minus B. And EM1 over J1 will be K divided by 1 minus A times Z minus B. And this is very simple algebra. You should be able to do it by yourself. I'm not going to do it right now. Okay, very simple. If you just plug it there and do some math you learn from middle school, you will be able to do it. Not that hard. Okay. Now, here in this simple model, how do the unemployment rate, vacancy rate, and aggregate output is determined? In equilibrium, it must be the case that the unemployment rate, U, is what? U must be the number of people who find the job, try to find a job, labor force, times 1 minus PC. PC is the probability that someone can find a job. 1 minus PC is probability that you cannot find a job. Divided by Q, that's the definition of U. But the Q goes out. So, and PC is this EM1J. So U is defined as 1 minus EM1J. And what is vacancy rate? Again, by definition, it should be the aggregate number of vacancy times 1 minus PF. PF is the probability that a job vacancy can be filled. 1 minus PF is cannot be filled probability. So by definition, the vacancy rate should be A times 1 minus PF divided by A. And the A goes out as well. So it becomes, so the vacancy rate is simple as 1 minus EM 1 over J1. And the aggregate output, remember in this model, it's very simple. Number of actual matches times each of those number of matches. Each of those workers who actually get a job will produce Z, right? So the number of total aggregate, that's the matching function times E, right? This is basically the capital M. M times Z will be the total production. Okay, and because this EMQA is a M is a constant return to scale, I can take the Q out. Everything in it divided by Q. So it becomes Q times E times M of 1J and times Z. Basically, we want to make everything in the form of the matching function. That's why we do this way. Because we know what's the here we are under the assumption that we know exactly what the matching function look like. Okay? And since we have the matching function, we know A and Q. Actually, we can solve for J already. So we already have the J. Then we will be able to easily determine EM1J and EM1 divided by J and 1. So UV are easily determined. And for the Y, Z and the efficiency, Z and the Q are also given here. So you can easily determine the aggregate output as well. So the equilibrium of this model looks like this. Okay. This is a little bit weird. We are not going to look at this graph first. We are actually going to look at this graph first. Because here, this K divided by 1 minus A times Z minus B, that's the equation that we gathered before. This is basically a constant. Right? K is a constant, A is a constant, Z and B are all constant. And this function, EM1 over J1, is also known function form. So given a constant, I can easily come down and get the equilibrium labor market tightness. Okay? And after the tightness is get, I can come back here to this graph. In this graph, now I change so here, I write labor force here. This is a little bit different and is very confusing to some students. So be careful here. The x-axis here is labor force. Okay, but now I change the x-axis here to be the labor market tightness. But here I keep it as the labor force. But remember, PQ, this function, it exactly described to me basically the relationship between J and Q. So given a J, I can always find a Q that's corresponding to that J based on that function, PQ. Okay? So that's how I then use this one to get the equilibrium Q star, the labor force. So in this model, the sequence of finding the equilibrium is I first find the labor market tightness. And then I plug this labor market tightness back to the P of Q function, basically. And there, because I have E times M of 1J and A and Z minus B and B, so I can know what is the expected payoff there. And based on the expected payoff, I can then know what is the Q. How many people, given that finding the expected payoff of finding a job is that high, what is the number of labor force that will come out and try to find a job, right? That's the definition of P of Q. Okay. And that's how I can get the Q. So from get the J first and use the J to get the Q. Okay, now I'm gonna do 3 different exercises or experiments. I'm also going to increase the UI benefit B and see what happened in this model when I increase the UI benefit. And then I will see what happened if we increase the productivity Z and what happened if we decrease the matching efficiency. Okay. The reason why we're gonna do this experiment for the first one is because we already do the same exercise for the one-sided model. Okay, and for this one, I can show you what happened in the two-sided model and see if what we can know in addition to what we already knew from the one-sided model. And the second one is because we already know that, at least from this textbook's point of view, most of this economic shock are driven by productivity change. So we're gonna see when productivity has some shocks, what happens to the unemployment market, the labor market. The last one is actually something we can use to explain the shift of the beverage curve that we talked about last week. Okay, so we'll come to this one by one. Okay. So the first one, increase in the UI benefit B. So for all these cases, I'm first gonna go through the logic one by one. I mean, it's really important for you to understand the logic one by one, but also important for you then to see the graph and understand how that operates. Okay, so I mean, what's really sort of difficult here, or might be a little bit tricky here, is that if you only look at the graph, you might lose some of the logic behind. And if you only look at the logic, you might get confused by yourself because it looks like something is affecting something else, and then this something else is affecting something else, then come back to affect these things as well. So it's quite not clear what happened there. Okay, so let's first at the easiest case, increase in the UI benefit. Okay, first, that increasing B will definitely reduce the total surplus from a match. That's Z minus B will be lower. And increase B must increase the wage, right? Because wage is A times Z minus B. That's the share of total surplus. And this one is lower, this one is fixed. So, I say, wait. Not from, like, see, this is where it is tricky. Okay, the logic is that, I mean, the intuition is that if the benefit is higher, it must be the case that I need to offer a higher wage, right? Because otherwise, I mean, marginally, some people would decide not to work. So the wage must be higher. Okay. And posting vacancy become less attractive to firm because right now, I mean, the benefit of actually get someone who work is lower. So the labor market tightness will fall. And for consumers, searching for work become more attractive as the wage is higher. But searching the work is also less attractive as the chance of finding a job is lower because J is lower. So you need to see the graph and see what's happening there in total. So in this case, Q actually may rise or fall given these two opposite effects. U rises and the V, and also the unemployment definitely will rise and vacancy definitely will fall. If that's not clear to you, let's look at the the equilibrium in terms of graph here. First of all, let's check this lower graph. This one, the relationship, the function EM 1 over JM1, this function doesn't change at all, right? And if you increase the B, this K over 1 minus A times Z minus B must be higher. So what happens is the market tightness will be lower. So in here, the market tightness will be lower. But this line also changed because we have B here, right? So if you increase the B, this thing also goes up. So what I mean is, if this thing goes even high, if this goes to even higher like this, so even the market tightness goes down, I could still get something that's this Q2 plumb. It could be the case that after the market tightness decrease, the labor force actually increase. But right now, the one that I show here is that after the labor market tightness decrease, the labor force decrease. Because the force that pushed the PQ, the expected payoff, goes up is not high enough. Okay. Okay. And remember, U and the V are EM1J and EM1 over J1. 1 minus that. So it is independent of Q and A. So after you get the J, you can already decide this. And if J, we know that J decrease, right? J decrease means this thing's decrease, but this thing's decrease, the whole thing will increase. This one is the opposite, so V must decrease. So you know that U rise and the V falls. Okay? So we get the same result as the one-sided model, actually. But in the one-sided model, I mean, the reason is different. We got a different reason why the unemployment benefit will cause the unemployment to rise and vacancy to fall. Remember there, we didn't even have vacancy, so the mechanism is all different. But both models give you the same prediction. Okay, and increase in productivity Z, this one increased the total surplus from a match. It also increased the wage as the worker get the same share of the larger pie. Profit higher, so posting the vacancy become more attractive. So labor market tightness must rise. For a consumer, searching for work become more attractive as the wage is higher and the chance of finding the work are better. So this one is actually easier. Everything's better. So Q rises, U falls, vacancy rises, and Y rises. So this one is actually easier. You see here, when Z increase, lowercase, the same thing happen. It is a moving along the curve. The market tightness also decrease. Sorry, the other way around. Sorry, because the Z is in the denominator. So when Z increase, the whole thing decrease. So actually the market tightness increase. Okay. And here when market tightness increase, but also this expected payoff, because there's a Z here, right? Z from Z1 to Z2 also increase this. So both this force make the Q increase to this level, the change in market tightness. And then because the whole thing move up, so it further increase to here. So this one is pretty clear that the labor force will increase. You can consider it as the whole economy is getting better. Of course, the labor force, there will be more labor force coming out. And given this, you can easily check that the unemployment will fall. And if the unemployment falls, the vacancy must rise because the only thing changes is the J. And if the J change, they must be working on the opposite. Because one is J and one is 1 over J. And the Y must rises because Q increase. And the EM1J also increase. Okay. Last thing is the decrease in matching efficiency. If it's the matching efficiency, the total surplus doesn't change. So the wage won't change. But the chances of finding a worker are now lower. So fewer firms post vacancy and J actually falls. Right? Because given the same number of people who find a job and same number of people who try to get an employee, the efficiency is lower. Efficiency is lower, there's less attractive for the firm to actually post a job. And consumer is also less attractive for them to search for a job. The wage is the same, but chance of finding a job is lower, right? So Q must fall. Okay. And the tricky part is that here U will rises, but the vacancy rate stay the same. And we will see why the vacancy rate stay the same. And because here, we will see rate. And the potential this is actually a potential explanation for the shifting beverage curve in 2009. We'll see why. Okay. So we're still looking at this graph first. What's key here is that this K divided by 1 minus A Z times Z minus B times Z minus B, this thing doesn't change at all because it is the efficiency that's changed. E changes. This is a constant that doesn't change. But this thing changed. Right? It has an E here. The efficiency is lower, so the whole thing goes down. And given the same level of this constant, it must be the case that the market tightness goes down. And the market tightness goes down here. And also, it has an efficiency here. This thing goes down. So this thing goes down, makes the Q goes down. And the J here also goes down, also make the Q goes down. So both force push the Q goes down. So in total, the Q goes from Q1 to Q2. Right? If this line doesn't change, then the new Q will be here. But because the whole line goes down, so it will be even further down. That's the key. So two forces both push the Q goes down. So the Q goes down. Okay, so this will increase the unemployment. Right? This will increase the unemployment. But the vacancy actually is not going to change. Because the vacancy is what? Vacancy is basically defined as we'll calculate it as this EM1 over J1, right? I mean, 1 minus that, but I mean, the calculation is only here. So vacancy is 1 minus this. But this is simply this, K divided by 1 minus A Z times Z minus B. These things is a constant here. So it must be the case that vacancy stays the same. Okay? The reason why I said that the unemployment and vacancy has a negative correlation is because this function, this EM of 1 over J1, this function doesn't change. Then this is a negative correlation function, right? The slope is negative. So it must be the case that when unemployment rises, the other thing falls, basically. But here, if we change the whole efficiency level, then the whole line is shifted. Okay, so this model can, in this way, if we decrease the matching efficiency, we can actually create such a scenario where the U is increased, the unemployment is increased, but the vacancy doesn't really change. So there are still that many job offers, but somehow not that many people find a job. So the unemployment is higher. This is the graph we see from the beginning of the class, last week, right? The negative relationship between V and U. Somehow after the 0809 recession, the relationship goes from here to here. So given the same level of vacancy, the unemployment is now higher. This model can explain this. Okay. And in the text, it has some further explanation. Basically, what happens, this is potentially an explanation, might not be the true story, but makes sense. Okay, so what happened in 0809 is a lot of people, 0809, how old are you guys? I mean, that's your elementary school or something? Okay, so you probably don't remember this, but back then it was because a lot of people in the US, they buy a new house, and you should know that if you buy a new house, most people don't pay cash unless you're super rich. So you take a loan. But this loan market get out of hand. A lot of the bank loan to those people who cannot repay their loan. And they even make this loan, put this loan into a more risky market. It's called the secondary loan market. Okay. And then the whole, some point there's a break in terms of some people started to unable to repay the loan, and then it has a chain reaction, then the whole market falls. So a lot of people have to basically give up their house after the recession. So a lot of people who even have to move from state to state, and they suddenly lose their job at once. So in that case, they're not easily matched with a new job because they have some skill that's really old skill, and they thought they can work for that job for their whole life maybe. But now they move to a new state, or even their old factories, they stay in the same state, but the new factory is closed. Their old factory is closed. They don't have the new skill to work in a new factory. So the matching efficiencies got that bad. That's one explanation. Yeah, you can look at the textbook for more detailed explanation of this. Yeah, I'm trying to recall my memory when I read the textbook, but might be slightly off here. But button up here, the key is that our model can explain this shift in beverage curve. And you should be able to operate the same logic here and check the results as well. Okay, so that's it for today.